Okay, so like this one here, cosine pi knows -1. Then I'm doing inverse cotan -1, which can be thought of as doing this, which of course would be back to what we have before. The problem is that each of these give different answers from a graphical perspective. Inverse tan -1, I know that happens in Q2 and Q4, but I'm going to give the answer in Q4 because that's the default range for inverse tan, for negative pi over 2 to pi over 2. So I give the answer as negative pi over 4, even though I know tangent of 3 pi over 4 is -1. But I have to give the answer like this. Now, cotan, because it has a different default range because of the graph. Because when we graphed inverse cotan, we restricted from 0 to pi. So then the range was from 0 to pi for the inverse. So I have to give an answer between 0 and pi. And where's cotangent going to be -1 on the unit circle from 0 to pi at 3 pi over 4? So that's a tricky one because the inverse cosecant has a similar default range to the inverse sine. The inverse secant has a similar range as the inverse cosine, except that you don't, do like pi over 2 or 0 because it's undefined for those places, whichever one you're dealing with. This one, however, they do have different default ranges. So you can't assume that the default range for inverse cotan is the same as inverse tan because of the restricted domain we had for the original tangent cotangent graphs. So notice what I'm talking about. So I'm trying to be very slow and deliberate because we're reversing things all the time. That's why this is a little more challenging of a unit compared to what we've done before. So that's the reason why. So you can't say this. You have to do that. But yet I do this like flipping of the inside or inverse cosecant and secant to make sense of it. Like for example, we had part B, or part C is a good one too. Like inverse secant of that. Well, I'm going to think of this inverse cosine just for my own sanity. So I could just kind of see, okay, where is the x-coordinate -√3/2? And then my default range from 0 to pi, which is the same for inverse secant, that's going to happen at 5 pi over 6. Now I got to do tangent 5 pi over 6, which is y over x. So the coordinates are -√3/2, 1/2. When I do y over x, I get 1/2 over -√3/2, which is -1 over √3. So I like to do this flipping just because it just makes it easy on me to see where to look. But I don't really think of the coordinates as this on this, something like this.
Yeah. Oh,
Yeah. So hopefully that clears it up. Okay. Very good. 71, yeah, sure, yeah. Let's do it. 71. Let's go all the way down to 71. Okay. Yeah. Ooh, good one. Love it. Okay. What you want to do here is recognize the fact that x is bigger than 0. So you're doing the inverse sine of a positive value. So you know you're in Q1. Okay. You could be Q1 or Q4 for inverse sine, but we'll be in Q1 because x is positive. By the way, for 74, if you're doing inverse secant, x less than 0, for 74, I'm going to be in Q2, just so you know. Because that. So you really have to be mindful of the volume, just so you know. But for 71, essentially what you're saying is that theta equals that junk, the inverse sine of 2x. So sine theta, of course, equals 2x. Sine theta equals 2x. Or 2x over 1, think of it like that. I'm going to do this in Q1. So here's my theta. That's a terrible looking right triangle. Just go with it. 2x and 1. And I'll call this A. So to solve for the horizontal leg, I do need to do Pythagorean theorem. If I do Pythagorean theorem, I should get √1 minus 4x squared. Because a squared plus 2x, parentheses 2x squared equals 1 squared. So that should be √1 minus 4x squared. I know I skipped some steps. I just kind of explained what I did, but did the Pythagorean theorem, right? Now I want the cosine of it, which is adjacent to our hypotenuse. So it's √1 minus 4x squared. Now, what if I, actually, it wouldn't have mattered, but what if I had x is less than 0? Of course, it's still positive because I'd be in Q4 because you're doing cosine. But what if I asked you, let's switch this up a little bit. Let me erase some of the stuff here. What if I asked you to find me the tangent of this function? Then, of course, it's 2x over that radical, of course, right? But then what if I said, no, x has to be less than 0. So now I'm in the fourth quadrant, and tangent's negative in the fourth quadrant. The answer would have been that. 2x over negative root 1 minus 4x squared. Because when you solve for a, you got to put plus or minus. So you have to be a little bit mindful. Actually, technically, the 2x would be negative, but regardless, you'd have to have a negative there. So you have to be mindful about that. If I switch the cosine to a tangent to x less than 0, I would get 2, 4. The tangent is negative 4. So when I did my Pythagorean theorem, solve for the radical, we have an option, plus or minus, when to solve for radical. Yeah, I know. Things get a little crazy there. So, other questions? You guys want to ask questions? Don't work.
So like for 75,
yeah.
do it in the second quadrant.
Yeah,
like,
exactly. Yes. And it's gonna be adjacent over opposite, right? Because we're doing cotan. Well, let's find out. So that's gonna be 3. No. Here's what's happening. Yes, x is positive right now, but because of that negative, so x holds a positive value, but that extra negative guarantees a negative number for this side.
Oh, okay.
Because x is positive to begin with, then we tack on the negative afterwards. So let's say x, for example, could be 5. Sure, great, 5. Let's say negative 5 because of the negative 3 over x. So I make that 3 because it's opening up. So anything that's opening up or right, I make it positive. Anything left or down, I make it negative. Just that's more intuitive. And then, of course, when I do my Pythagorean theorem, I get root x squared plus 9. So if I want the sign of it, it's going to be negative. Sorry, it's going to be 3 over root x squared plus 9. And it guarantees a positive outcome because it's the way it's set up. So that's the kind of question I want to ask about inverse tan stuff or inverse trig stuff. I want to ask these kind of questions. Definitely expect a question like this for sure. That for sure I like. And we're going to start moving the problems like 78, 79, 80, because we're going to start solving equations in just a moment. We're going to do that very shortly. Okay, other stuff you guys want to ask about? Anything else? We're okay? We're cool? Yeah, go ahead. Oh, great question. Inverse cosine. The default range is 0 to 5. Because we restrict the domain from 0 to 5 from cosine. And that's negative. X is positive, but there's a negative. So this whole embodiment, this whole input is negative. So I gotta be Q2. Correct. 100%. That's why I did the graphs, so you can visualize it. That's why I did the graphs. What's probably best is look at the graph of cotangent, restrict that domain. What domain would we want to restrict? 0 to pi. Hence, that would be the default range for the inverse cotan. That's what you want to do. Ever good?
Doing the x in the wrong place, like because isn't it like adjacent over opposite? So what is adjacent be 3 and the x be the opposite?
Oh crap, you're right. Darn it. Yes. Thanks. You are correct. My apologies. So the answer was x over. Correct. Thank you. See, I'm human, guys. I make mistakes. Thank you for correcting me, Avery. But that would have been like a careless share. That would have cost. I'd take up a point for that. So I made a mistake. Yeah, thank you. My apologies. Someone's paying attention. Okay. All right. Hope to make no more mistakes later today. So, all right. Other questions? No? All right. Let's move on. Let's finish off the rest of the notes. And then I want to give you a new set of notes on chapter 5. Because we do have to start talking about identities. Actually, the identities you might like, because that's kind of like a puzzle. And we're going to talk about that later today. But first off, let's talk about writing solutions or getting solutions. Okay. So, we're going to finish off the notes here on page 31. And yeah, If you told it a equals the inverse sine of √3/2, well, I know the answer has to be just pi/3 or 60 degrees. Remember, it's just one output. Using the default range. Or inverse sine. Okay, that's what's happening. Just one output using default range numbers. But look at what the next question is asking. This is an equation. You need all possible answers. So if you think about that one, what are all the possibilities that makes that true? Yeah, thank you. However, is that it? Yeah, you go around. So are there infinite possibilities? Yeah. So here's what you would write. You could write pi/3 plus 2n pi and 2 pi/3 where n is any integer. And we call this a general solution. Because in general, this is what we expect. And it follows this format. So pi/3, 7 pi/3, 13 pi/3, 19 pi/3, 25 pi/3. I'm just adding 2 pi/3 over again. Or I go backwards, pi/3, negative 5 pi/3, negative 11 pi/3, negative 17 pi/3, negative 23 pi/3, and so forth, right? Or for 2 pi/3, 2 pi/3, 8 pi/3, 14 pi, I might be 20 pi/3, and so forth. So you just do this over and over and over and over again. So that's called a general solution. And that's what we're trying to do here. And then sometimes I might ask for specific solutions. Like I might say, hey, find me the first 3 positive solutions, or find me the 4th negative solution. So then you have to then understand the general solution and then use that to find a particular solution afterwards. So let's try this for example 1. Because remember, for a equals inverse sine of √3/2, I'm treating it like a function. I want one output. Doing inverse, but for an equation, I want all the possibilities. It's kind of like, for example, if I asked you to find root, it's analogous to this, right? If I said find me √25 or x squared equals 25, for √25, what would you say the answer is? Just 5. You don't say plus or minus 5 because you want the square root function to be a function, right? You want just one output. You wouldn't do this. That's a sideways parabola. That would not be a function. You only want to get one output. But here, you want to give all the possibilities. That, of course, that would be plus or minus 5. Because from a graphical perspective, what's happening from a graphical perspective? You graph y equals x squared. You graph y equals 25. Where do they touch? Twice. So you got to give me both answers for an equation because you're trying to connect this graphically algebraically, right? But this one, the inverse sine, we know that graph of inverse sine is just, I already forgot how it looks, but it's kind of terrible. But anyhow, you get the idea. Like I want one output. Same thing here. When I have sine B, you know what sine looks like. That goes on forever, right? If I draw a horizontal line, how many times that horizontal line touch this graph? If I draw a horizontal line at y equals √3/2, which is slightly less than 1, it's like 0.8 something, how many times are they touching? So I got to give infinite possibilities. I have to have an answer that generalizes that. That's what's called a general solution. So that's, hopefully you guys understand that difference now. That's why I have to give more answers than one. Kings, go ahead.
So is it when you're like solving for the inverse of a function, you only get one that?
Right, if you're evaluate and solve. That's the difference. If I say evaluate, give me one. If I solve, give me all. Give me the whole thing. I want to solve, not evaluate. So here we go. So cosine x equals √3/2. Great. Where does that happen? At pi over what? And great, awesome. So you're gonna write this. Those are my general solutions. Now to find the first three positive solutions, well, pi over 6, 11 pi over 6, and what's the other one? Yeah, good, you got it, yeah. There you go. Okay, now I think you guys are kind of getting the hang of this. Try example 2. What do you think? Actually, let me do it with you, never mind. Why is example 2 a little crazy now? What's happening here? Yeah, let me do it with you. Actually, I just realized. Let me do it with you guys. It's a little crazy with 3x. Oh, he did? This one? That's mean. Okay, now you'll know. I'll show you. I'll teach you guys. Okay. Okay. I know you guys are traumatized. That's all right. You'll be okay. Okay. So 3x is going to equal. So the angle right now is not x, it's 3x. So 3x is going to equal the inverse sine of this, but we have to find where is the y-coordinate in the circle negative root 2 over 2. That should be at Q3 and Q4. So that would be 5 pi over 4 and 7 pi over 4. And by the way, when you give these answers, start with this interval. Give me all the possibilities within the first rotation. Do that first. Okay, that's what I suggest. Do that first, and then you'll be okay. So 3x will be 5 pi over 4 plus 2n pi. And 3x will be 7 pi over 4. Plus 2n pi. We're okay with that? Cool. So now what do I do? Let me move the screen. Give me a sec here. Okay, so it's really easy. You didn't know last year. Now you're going to know. I want to solve for x, so what should I do? Divide by 3. So it's 5 pi over 12 plus what? 2n pi over 3. Yes, exactly. That will be a catch-all. It will encompass everything. And then, of course, x will equal what else? 7 pi over 12 plus 2n pi over 3. So as you can imagine, there's going to be several answers in that first rotation. So 5 pi over 12, 7 pi over 12. And then think about 2/3. What's 2/3 as a new fraction of 12 in this denominator? That's 8 twelfths. So 13 pi over 12 4. That's still in the first rotation. 13 pi over 12 4. 15 pi over 12 4. Add 16 to that. You can do 8 pi over 12 and do it again. 21 pi over 12. 23 pi over 12. There's so many possibilities. And by the way, there's 3 pairs. Why are there 3 pairs? What's your angle? 3x. Think about it. You have 5 pi over 12, 7 pi over 12, but you totally could get these other answers. Actually, let's do this. Before I answer this question about the first 3 negative solutions, let's go to Desmos. Desmos is going to really kind of tie things together for you guys. So, y equals, I'm just going to do sine 3x. I'm not going to write the whole equation. And y equals negative square root 2 divided by 2. So many possibilities, right? Oh, look at that. And then, you know what? Let's switch this up. Let's make this nice. Negative 2 pi. 2 pi. Step is, we'll do pi over 2, I don't care. Whatever. We're in radian mode, of course. Yes, very good. Okay, let me clear that for a moment. Isn't that lovely? Isn't Desmos great? And see, gives me those answers also. 5 pi over 4, that was 15 pi over 12, by the way. Which makes sense, right? Because that's a difference. 5 pi over 12, 15 pi over 12, there's 8 pi over 12. 2 pi over 3. 8 pi over 12, 2 pi over 3. 7 pi over 12, 5 pi over 4, 7 pi over 12, and 15 pi over 12. The difference is 8 pi over 12, 2 pi over 3. Have I done a full cycle yet of the sine curve? No. Because my period is, well, actually, I have technically, but have I gone from 0 to 2 pi yet? No. Obviously, I've done one full cycle because the cycle is now 2 pi over 3. That's why there's so many answers from 0 to 2 pi. You can see there's even more answers, right? But how do I have this catch-all? How do I kind of encompass all of it without going crazy? Just do what I did here. Just do that. Just imagine that 3x equals that. So let theta be 3x for a while. Great. Okay, now solve for x divided by 3. And that'll cover everything. Everything will be covered. You don't have to write any more than that. Now, the first 3 negative solutions. Of course, I go back to Desmos and find out for myself. Like, okay. Let me clear the screen for a moment. Those are my negative answers. Negative pi over 12, negative pi over 4, negative 3 pi over 4. What if I do this without a graphing calculator? I am going to do that. Sorry, I am going to do that to you guys. How do I do that without a graphing calculator? And the reason I'm doing that is because you're going to expect to know that in AP Calculus, right? So I want to train you guys to think that way. So if you think about it, let's go backwards now. Let's let n be negative 1. So what I like to do is like let n be negative 1, let n be negative 2, and see what happens. If n's negative 1, I'm going backwards 8 pi over 12. So that's going to be 3 pi over 12, negative 3 pi over 12. You guys see how I got that? Because 2/3 is 8/12. If I'm subtracting 8/12 from 5/12, negative 3/12. You can reduce later. I don't care. Likewise here, if I plug in negative 1, that'll be negative pi over 12. And then if I do this one, go backwards another 8 pi over 12, that's negative 11 pi over 12. And this one, go backwards 8 pi over 12, negative 9 pi over 12. So what are my first 3 negative answers? Correct. Those are my first 2 negative answers. Correct.
Are you only using one of them? You don't have to like.
No, I use both.
Yeah.
I use both. When I was negative 1, I calculated both of these. When I was negative 2, I calculated both of these.
Oh, and you just picked the first.
The first 3 negative ones, correct.
Got it.
That's
Right. Which naturally, this would probably be the first negative one because it just cracks the negative barrier, if that makes sense. For n is negative 1. But yeah, that's what happens. So this kind of thinking, like this abstract kind of thinking a little bit, is what we want to train you guys to think like, because that's what's needed for success in BC calculus, right? We want that kind of thinking. So negative pi over 12, negative 3 pi over 12, negative 9 pi over 12. You can reduce it afterwards. I don't care. If you don't reduce it, I'm not going to hold that against you. I'm okay. Okay, let's try another one. Let's try example 3. I'm going to try on your own. You guys can handle it. And also example 4. Example 5, we definitely need a calculator. And then example 6 will wrap up the chapter 4 notes. And then I want to start talking about review of identities because we got to talk about that too today. Oh, I hope people are not getting sick again. Don't want cold flu season. Okay, so just so you know, you're going to subtract 1 and divide 2. It's going to get you guys started.
Yeah. Well,
Cool.
oh,
What do you guys think? Pi over 2 pi over 3 and? Good.
How do we get there?
Subtract forward by 2. And then do the inverse cosine of 1/2.
Oh, okay.
Yeah, subtract 4 by 2. That's, yeah, 2 pi over 3 and 4 pi over 3, I agree. Then just solve each one separately. Oh boy. What's that going to be? Lovely fractions. Pi over 6, I think. Because you convert that 4 pi over 6 to 3 pi over 6. And that one, 5 pi over 6. Even more lovely. Look at that. Four. Okay. I mean, no, I did forget to write 2n pi initially, but a 2n pi only gets impacted when there's a coefficient in front of x. I mean, if you're adding a number to x, that doesn't matter because you just combine it with what's on the other side. But when you divide by 4, 2n pi must also divide by 4. That's what you get pi 2, pi 2. There's a lot of stuff.
What was the step after we found like where cosine is -1/2, and then what did we do after that? Like,
Oh, sorry, sorry.
after, so the next line, like, we found where cosine is -1/2.
Yes, correct, yes.
And then what's after that?
Well, after that, I subtracted pi 2.
From.
2 pi over 3, yeah, so I did 2 pi over 3 minus pi over 2. So 2 pi over 3 is 4 pi over 6, and pi over 2 is 3 pi over 6. So you just gotta find the LCD, the big difference. And likewise for 4 pi over 3 minus pi over 2. Yeah, sorry to show that.
Okay.
Yeah, it wants to track pi over 2. I know, I have professors that just did a bunch of stuff. I'm like, oh, okay, yeah, I'm like, I didn't. So thank you for asking. Be about having a small class, you can ask it. I'm a much nicer teacher than a professor doesn't like want to be asked questions. Looks good. Oh yeah, go. Okay, guys, try example 4 now. Oh, we need to find 3 positive answers too. Sorry. Very first 3 positive answers for example 3. Yeah, good. I would agree. Yeah, what's up? You're gonna add so the first 3 positive answers are what you see. Then you go and do 1. Right,
Yeah.
find the LCD. Pi 2 is 12 pi 24. Yeah, so fractions.
Yeah, so.
Sorry.
No, we want to find the first 3 positive solutions as part of the question. So the first 2 are pi over 24 and 5 pi over 24.
Yeah.
And then I'll let n equal 1 to find the next set.
Okay.
And when I let n equal 1, I'm adding pi over 2. But when I add pi over 2 to pi over 24. So it becomes 12 pi over 24.
Okay.
And then it becomes 13 pi over 24. Oh, look at that one. Liking that. All right. You guys try example 4 now. And I'll do example 5 with you guys because that one's a little funky. So undefined, if you think about it, Wouldn't that make sense? If secant's undefined, that means that the cosine was 0. Right? And remember, we're not doing any inverse just yet, just go for secant and cosine, you don't flip the inside. You don't do that, just, cosine goes to 0. That's gonna be at pi over 2 and 3 pi over 2.
Yeah.
Yes, undefined at pi over 2 plus 2 and pi. If it helps, maybe make a barrier like this and just solve each one individually. So you don't get to. That helps. And then you got to multiply by 2, or multiply both sides by 2/3.
Okay, we'll do this alright.
Would you agree with what I have in red? Yep, multiply by 2/3, isolate the x. Find the. Now, I'm not asking for the first 3 negative answers. I'm asking for specifically the third negative solution. But I specifically want the third negative solution. So if I plug in -1 for n, I should get negative pi or negative pi over 3, I think. If I plug in n equals -2, should get -7 pi over 3. Or -5 pi over 3. Am I correct in doing that? Hold on. Yeah, I'm correct in saying that. So what's my third negative answer? There you go. That's my third negative answer. So the strategy, notice I'm very methodical about this. Switch secant to cosine, make it 0. Figure out what happens. Do plus 2 and pi, both sides of this isolate x. Update that. Then plug in -1, plug in -2 to see where we can get a third negative answer. So I got my general solutions and I got my third negative answer. Okay. Okay. All right. Now let's do example 5. Now this one you're gonna need a calculator. So you may want to get a graphic calculator if you have, or scientific at least. And this one, you don't necessarily have the safety net of like thinking about unit circle. So you really have to trust the calculator. And I got it myself, my own little, actually there's a cool TI-84 app. Ms. Wong has sent it. Let me see here. Yeah, there we go. This is pretty nice. Hold on. Leave. Goodness. All right. Okay. So let's look at the problem first. The problem is asking to solve for x, of course. Find the general solution, the second positive solution. So this is a little funny. Sine of x plus 1 equals -0.7. So x plus 1 will be the inverse sine. Okay. So it's a little crazy here, but bear with me. We could deal with crazy. So let's make sure we're in the right mode. Yes, I am. Inverse sine of negative 0.7, negative 0.7. Okay, let me clear my screen for a moment. So quiz give me a negative answer, right? Okay, so what quadrant is that? You guys get that?
Do we have to be in
Yeah.
radian?
Yes, 100%. Yes. I will make that requirement. So what quadrant is that in?
Q4.
Q4. So if you think about the reference angle, and this is the part that is a little mind bending. Even this is calculated aloud, I would argue this is a little harder than the other ones we've done so far. That's gonna be right over here. So your reference angle is 0.775. And sine's negative. So if I think about from a positive angle perspective, if I'm rotating this way, counterclockwise, when would I expect the same thing to happen? Definitely here. And definitely here. Right? So my reference points, even though it says negative 0.775, that's my reference angle. So if I do a half rotation and add the reference angle, or do a near full rotation, but take away the reference angle, what do you think these two angles will be? What do you think is going to happen? So pi plus 0.775 and 2 pi minus 0.775. And because they're asking for general solutions, I'll put plus 2m pi and plus 2m pi. So what I did was I solved it like I would in the equation. Did my inverse sine, but I used calculus. I can't do inverse sine of in my head. Got that great. But then I try to visualize it as a sketching angle in standard form. Like, okay, have that. But let's adjust that so I can get the answer from 0 to 2 pi. Let's adjust it. That's what I did here. Okay, and it's here and here, Q3, Q4. So half rotation plus 0.75 or full rotation minus that. That's why I put pi plus 0.75, 2 pi minus 0.775. And of course, in a general solution, I can do that. Now, if I want the second positive answer, of course, I'm going to go with 2 pi minus 0.775. That's the second time it becomes positive. So I'll state that as my answer for the second positive solution. Oh, you can. I don't care. You can leave it that way. I don't care.
Well, it's just that it's X department, so we've got stop there. Well, subtract one.
Oh, shoot. Darn it. I got to subtract one, guys. Sorry, my apologies. My apologies. I knew it's too good to be true. I knew I was going to make a mistake. Thanks, Charlie. You guys understand that? I forgot to subtract. X plus 1 equals this junk. Yeah. I was almost there. You know what? I just forgot the last step. Forgot to subtract 1. So you gotta do minus 1. Correct. Yeah, so if I were to give it as a decimal, actually I should probably give it as a decimal now. The more I think about it. So if I do express as a decimal, it should be, that's when now I'm gonna get my graphical calculator. My hand helps me much easier at this point. Pi plus 0.775 minus 1. So 2.916 or 917 plus 2m pi. Or the other one, 2 pi minus 0.775 plus 1. Not minus 1. 4.508. Okay. Yeah. There we go. And you can always check it out. If I were to do sine of what was it? What was the equation again? It was 3 plus. 3 plus sine. Got it. Yep. So if I did 3 plus sine of 2.917 plus 1. I get 2.3. Yep, I get 2.3. There we go. Yep. Yep. So that's how you want to do it. So definitely have a chance to practice that, and we'll have to talk more about that next time. Let's look at example 6. Yeah, looks good. No, I will do 2 parts. Oh, yeah, of course. No, I'm doing 2 parts. Yeah, no. Nice try. Okay. All right, last one, guys. Example 6. You're asked to write 2 equations, one involving cosine, one involving secant, that produce a graph on the right. Okay, let's write as a let's write as a cosecant. So think of it. It's like sine, but obviously it's not sine. So you can do a cosecant bracket b x minus h plus k. Now, is there any vertical shift here? Nope. What's the amplitude? What's the period? So 2 pi over b equals 8. B is going to be pi over 4. Is there any horizontal shift for sine? Because sine starts here. It's all good, right? No problem. Let's write as a secant. So 2 secant, same period. So same b value. Of course, k is the same. But secant is like cosine. So you want to start at the peak. Where does the peak start at? So x minus 2. There you go. And it should always be shifted by pi over 2. If I just do that pi over 4, you get pi over 4 x minus 2 pi over 4. So I shift by pi over 2. Those are complementary and stuff like that. Those should be pretty straightforward. Of course, I can always twist these questions, and I can say, hey, give me a value's negative and h value's negative. I could do that. I might. Where because there's no condition for a or h, I kind of just left it open-ended. So I just chose something that seems simple, right? Oh, if I do it as a is negative, I'd start over here. I still don't know what that means. If I do for a cosequence. And then of course, 4 by 1 and a is negative and h is positive, I would start over here. So I'll make sure you guys get that practice. Yeah, you'll see my old tests what they're designed, so you guys have the practice. Okay, we still got some time left. I want to briefly talk about identities. So yeah. Yeah, I would just say just to avoid any confusion. It's always good to check. But I would just see it as and just take that piece of value. Yeah, I would. Okay, we're gonna briefly talk about identities. We'll talk more about it. Yeah, see you guys tomorrow. Yeah. Oh, you're having this on. This should be online.
Yeah. I'm starting new list.
I'm just gonna briefly talk about identities for a few minutes.
I don't understand.
Oh, yeah.
And also,
The chat fund.
Yes. Pass this out as well.
You're sorry. Yeah, this one's 60.
Oh.
All right, so let's briefly talk about identities, just so jog your memory a little bit. All right. Okay, an identity means the left side is identical to the right side. That's all it ever means. So you guys should already know cosecant, secant, cotan, how they're related. You know, hopefully tan and sine of cosine, like y over x in a new circle, cosine like x or y in a new circle, so cosine of sine. Those should be pretty standard. I'm not teaching any new identities in the next 7 minutes because that's crazy. But remember Pythagorean trig identity? Remember that? And that is true because the Pythagorean theorem. A squared plus b squared equals c squared. It's not like x squared plus y squared equals 1 squared. Because x and y are the sides on the triangle and the circle, one's hypotenuse. How do you get the other two variations, by the way? What? It's yeah, divide by sine squared or divide by cosine squared. Correct. You can get those other variations by dividing both sides by sine squared or cos squared. And again, why does that make sense? Because when you think about the unit circle, again, that's cosine theta. That's sine theta. That's one, whatever. Right. Okay. So you guys should be fairly comfortable with simplifying. Like, for example, I'm just gonna kind of gloss over these. We'll spend more time on this, don't worry, tomorrow. But like cotan is one over tangent, right? So when you simplify that, what do you get? 1. Up top, you could rearrange it like this. So by doing a simple rearrangement, we'll do those first two trig expressions out to. So you have 1 plus tan squared x over secant x. And there's a variation that involves 1 plus tan squared. Secant squared x, correct. Right up above. So you secant x.
Well.
Okay, cool. You guys quiet? Thank you. I'm just gonna jump around a little bit. Just kind of curious how you guys take to this. Go ahead and try simplify examples 4 and 5. This will be our last two we'll do. We'll stop there for today. We'll do more of this on Thursday. So example 4. You guys, we got like 2 more minutes. Example 4. Can you back something out? Sin x. And for example 5, what's going to be your best approach? Maybe FOIL? Yeah, maybe FOIL. Yeah. Yeah, so when you do identities, you're just doing algebraic skills, really. That's what you're doing. And you just gotta get a little creative sometimes. Yes and no. These ones you're seeing right now, no. But with some of the newer ones, yes. Like the sum and difference formulas, that's what the new ones we'll talk about tomorrow. I think I should give that to you. But the other ones that you derive from it, that I'll expect you to derive on your own. But I do give some. Some I do give. The non-monster, I do give some. Yeah, I'll talk about those as well. You guys get sine X for example 4?
It comes to that, it's like it can be, it's like, yeah. But that's not simplified with their sign. Oh, right. And we wouldn't almost back this.
Yep. And it should be, it's called simplified for a reason. You want to make it look simple, right? That looks kind of crazy right now, simplified. Simplified six for X. Example 4 sine X. Wait. So just kind of get you guys to think about identities again. The homework will be a combination of chapter 4 and 5. So I'll put a handful of problems from chapter 4, like this all good play. And then some identity stuff. I'll put on school G the next half hour, so you guys know what it is. All right, I think we're all set. Cool. Welcome.
I feel like it must have started the second show. Also, I just. Like, for the French class, I wrote instead of they are. I hope that actually, they're like, that would be so much more.
Welcome. See you guys.
I thought it was stat, but he said stat in French. No, that's the definition. Isn't it? How's that stat? It's trees. Trees.